All right. Well, welcome to our last CSE215 class, um, and let me hop onto Canvas and take a look at what we got here. Alright, so I got 18 homeworks turned in for homework 9. So if you didn't turn in homework 9, do it right now, like within the next 60 seconds. Because I'm planning to go through that homework extensively in class, and then I'm definitely not going to take any late submissions after that. So if you get it in like in the next, 45 seconds or so, I can take it those few minutes late. And it's a double point homework, so it's a good one to make sure you turn in. And so I want to start with questions that people have, and then I want to talk about the homework, even if people don't ask specific questions. I want to make sure we go through all of those because we're not going to have another class meeting after I've graded your homework. And I'll probably only grade one question from the counting unit and one question from the automata unit. So I want to run through all of those in detail. And then I want to just kind of talk briefly about the final exam, remind people when it is and so on, and then just kind of do a course wrap-up. But let's start with any questions that anybody has.
Yes, I did have a question on number 1 on the counting, just more of the format that you wanted the algorithm to be in.
Okay, let's see. Oh, for the recursive algorithm. So that was one that I said let's just kind of like think about it,
Okay.
and play around with it a little. So let me pull this up. So outline a recursive algorithm for computing n factorial. So did you come up with something?
Yeah.
What did you come up with?
I wrote mine in like pseudo C. Is that fine?
Sure.
Okay, cool.
So what's it look like?
So I said like I basically just created a method called rec, passed in n, and said that equals n times rec n minus 1, and then if n equals 1, then basically return 1.
Cool.
Awesome.
So if n equals 1, return 1. Otherwise, return n times rec n minus 1. That's a good recursive version of a factorial. And we could write that mathematically like this. So you'll see stuff written like this sometimes. And it says we can use this in general, use this as a base case.
Gotcha.
Cool, sounds
I
good.
did the same thing, but I went all the way down to 0. Is that fine?
Yeah, that's fine. So you can also do this as 1 if n equals 0. This if it's bigger than or equal to 0, because then 1 factorial will be 1 times 0 factorial, which is still 1. So that works too. Have we talked about why 0 factorial is equal to 1? Like why multiplying nothing gets you 1?
Briefly. We've talked about it briefly, but I understand why.
It's a little bit like, this 1 to the 0 is equal to 1. I mean, the exponent of 0 means we're not multiplying it by anything, right? You're not even multiplying it by itself once, but yet somehow we still end up with a 1 out there. And the basic explanation is that this is what makes things work. This is what makes things work. If we didn't have this fact, then factorials wouldn't work in some very profound ways.
There is a less mysterious explanation.
What's that?
If you think about what a factorial is, it's like the previous factorial times the new number. So 6 factorial is equal to 6 times 5 factorial, right?
Mm-hmm.
So you could equally say that 5 factorial is equal to 6 factorial divided by 6.
Ah, okay.
And so you work that down. 2 factorial is equal to 3 factorial divided by 3. 1 factorial is equal to 2 factorial divided by 2. 0 factorial is equal to 1 factorial divided by 1.
Right. That makes sense. So what is negative 1 factorial equal to?
Yeah.
So negative 1 factorial would blow up.
No.
Interesting.
And in fact, that is what negative 1 factorial is. It's actually equal to, well, it approaches both infinity and negative infinity.
Yeah, I got a neat little math error on my calculator.
Yeah. And so there's this thing called the gamma function. The gamma function is this definite integral. It's an infinite integral. And gamma z is the integral of x to the z minus 1 e to the minus x. And this function has this marvelous property that gamma n is the same as n minus 1 factorial. And so if we find gamma 1, that's going to be equal to 0 factorial. Gamma 1 is right here, and that's equal to a 1. And gamma 0, which is negative 1 factorial, well, it blows up to both infinity and negative infinity. And in fact, at all these negative integers, the gamma function blows up. And it's actually undefined because depending on which way you approach 0 for the gamma function, minus 1 for the factorial, you either get larger and larger or you get smaller and smaller. And so it's undefined unless you wrap your plane so top and bottom are connected. But this is a what we can call a continuation of the factorial function. It's a function that's defined almost everywhere, but on positive integers it agrees with factorials. And so we can think of it as some kind of analytic continuation of factorials. And it's got some other cool properties, particularly when you look at non-integer factorials this way. We get some cool values. So in particular, gamma of 1/2 is the square root of pi. So that's like, 1.5 factorial is equal to the square root of pi. Why is that? I don't know, but you gotta love that idea, right? That like this thing that comes from circles and square roots, which are kind of weird to begin with anyway, are tied into this function that we normally get just by multiplying consecutive integers. And so there's this connection here. And and you can get cool graphs if you look at the derivative of it. So the derivative of a factorial, right? What's that about? So this is how the function grows. And this really quickly gets you back to the Riemann zeta function, which I mentioned a while ago in the number theory unit. If you want to lose a few days of productivity, dig down that rabbit hole, and there's some really amazing stuff there. So yeah, factorials are a more complex function where we only look at it on positive integer values or maybe 0. So yeah, anyway, that would be a good, either of those would be good for question 1. Interesting.
Have you ever seen that before?
I have not.
Figure that's awesome.
All right. So somebody just posted this in chat. So this is called Tupper's self-referential formula, and it's this formula, right? And if you graph it, this is what the graph looks like, which is awesome. love that.
The coolest thing I've ever seen.
Yeah.
One of. I have no idea how on earth you'd figure that out.
Oh, lots of good music and good food and stuff. So while we're in here, let me toss out this idea. I've mentioned this usually at least once in the CS sequence of classes. So here's a challenge a friend posed to me back in the summer of 1986. And the question was to write a C program, right? Call it, program.c. And, you can put whatever you want in here, but when you run this program, what it should print out is the exact copy of its source code. And you're not allowed to just open program.c and read each line and print it out. This has to be a self-contained program with a bunch of print statements, basically, that when you run it, it prints out the exact source code for itself. And if you've never thought about this, I recommend thinking about it. Again, when you got some time to kill, or you want to break.
It'd get infinitely larger, right?
It can if you're not careful, but there is a way to do this in a nice self-contained program. And I suggest not Googling it because there's lots of information online about programs that do this and characteristics of them and so on. But it's a fun challenge to think about, particularly as, we're talking about recursion in 222, recursive functions in here. Kick it around sometime if you're curious, right? What would it take to write a program that prints out, each line of its own source code in a self-contained way? And it is doable. And discovering how to do this is something that kind of defined the direction of my life for the past few decades. So it's a fun thing to play with. Not related to CSE215 directly, but still fun to play with. All right, other questions? Thanks for posting that formula. Other questions?
Could we go over languages number 8?
Yeah.
I think I got it, but I'm not too sure.
All right, let's see what we got here. Design a Turing machine that, given an arbitrary spring, replaces the first 2 consecutive ones with zeros. So we want to find the first 2 consecutive ones and replace them with zeros. And as I said last time, this isn't rigorously defined as to what do I mean by the first 2 and where are we starting from and so on and so forth. And so I suggested just assume you're starting with, the beginning of a bit string, and by first 2 we mean the first 2 going in this direction, so the 2 least significant consecutive zeros.
I totally misread that.
What did you do instead? Because it's probably still right.
2 consecutive 1 and 0.
Oh, that's fine. Same idea. I mean, if you can do that, you could do the other.
Yeah, so instead of 1 1 or 0 0, it was the first consecutive 1 0.
Okay, that's fine. Yeah, it won't change the basic algorithm. Just the details.
Which one is this? This is the Turing machine?
This is question 8, yeah, from the second batch of homework questions.
Okay, yeah, that one is pretty interesting. I figured out a pretty cool way to do it.
Okay.
Probably actually every way you do it.
So what's a basic algorithm? Forgetting about the details of a Turing machine, what would be a basic algorithm or a series of steps we could use if you were just describing to somebody how to do this, but they weren't very sophisticated? What sort of instructions would you give them?
I mean, if we knew we were on the far right, then just keep going and to the left until you find and copy each bit that you encounter until you find 2 ones.
Wait, did we start at the left or at the right?
Did not specify, and so my suggestion was make an assumption and just say what your assumption was, or maybe it'll be clear from the way you wrote it up. So I'm just going to do this starting from the left, but if you do it from starting from the right, it's the same algorithm. It'll just be, opposite directions.
If you start from the left, shouldn't you move right?
If you're going to start from the left, you're going to move right. If you start from the right, you're going to move left. But the sequence of steps is going to be basically the same, right? start at one position, move towards the other end, and copy the bits as you go, but be on the lookout for 2 1s. And you won't know if you found 2 1s until you get to the second one. And so at that point, you know, change the 1 to a 0, move right, change the 1 to a 0, and then you're done. And that'll change those 2 1s to 0s. So the stateful part, the most stateful part is this business of looking for 2 1s. Because when we get here, you know, we find a 1, we don't know that we've got 2 1s yet. So we need to record the fact that we just saw a 1, and we do that by moving to a different state. That's how we record all information in a state machine. We'll go to a different state, which means, hey, we've seen a single 1 so far. And then if we see a 0 next, we go back to our original state. But if we see a 1, now we know that we found 2 1s. So how could we code that? And so yes, question 8. How could we code that? Start in the state S0, and if there's a 0, we'll stay in state S0, write a 0, and go left. And so my comment here is, you know, look for a 1. If we're in
question.
Yeah.
So for question 7, I drew like a state diagram or a state transition thing, like the S00 whatever. But for 8, I just drew it. Is that fine?
Just drew the state.
I drew the with the arrows and with the commands or whatever.
So we're looking for a set of instructions for the Turing machine, basically. If you're drawing circles with arrows, that's a state diagram.
Well, shucks.
But there's still value in either, right? Because going from a state diagram to a Turing machine or the other way, it's pretty straightforward. I mean, it's mechanical at least. These are just different ways of envisioning how we use state to run an algorithm. So if we're in state 0 and there's a 1, we need to record the fact that we've seen a 1. So we'll go to state 1, but we're going to preserve that 1, and we're going to move left. And maybe if we're in state 0 and there's a blank, then we'll go to state, 99, and we'll leave the blank and we'll go left. And this will be where we end our program. We'll halt our machine. And so my comment here is, done. Here we see a 1. So state S1, we're looking for a second 1. So if we're in state S1 and there's a 0, we found a single 1 but not another 1 next to it. So we're going to go back to S0, we're going to leave the 0, and we're going to move left again. And so here I'm going to say, try again. But if we're in state 1 and there's a 1, now we found, a 1 and we found another 1, we're sitting on top of this one. So now we're ready to change these 2 bits to 0 and finish. So I'm going to go to state S2, I'm going to change this 1 to a 0, and I'm going to go right. Change the second 1 to a 0. And if we want to be complete, we could say if we're in S1 and there's a blank, well, it'll halt automatically. So S2, we know there's going to be a 1 under here, right? And so if we're in state S2 and there's a 1, we'll go to our halt state, we'll write a 0, and it doesn't matter which way we move, left or right. And that'll change this 1 to a 0, and then we'll go to an undefined state. So something like that would get us there.
I did something slightly different where the first 1 I saw, I changed it to a 0 right away. But then if the next, then I move 1 to the right, and if that is not a 1, I move back 1, turn that back to a 1, and then move back to the initial state.
Okay, cool.
At the next integer.
Yeah, that works too. So just like C, there's usually multiple ways we could do whatever we're trying to do. And just like C, you know, I think people probably begin to develop fingerprints or signatures for how they code algorithms on, say, a Turing machine. And usually we don't write, you know, practical code on a Turing machine, but you could. You could write a tic-tac-toe game on a Turing machine. You could make a web browser, or you know, an interactive video game. Say again?
You could make a Turing machine.
You could make a Turing machine, and in fact, you should.
That's how they pass the Turing test, right?
Yeah.
It can write itself.
Yeah, I mean, first thing.
Have you ever heard of the game of life?
Yeah.
Yeah, it can write itself. It's really cool.
I think von Neumann was the first person to come up with a self-replicating network on a game of life, and or at least with cellular automata. Game of life is a version of that. But yeah, I mean, and this is related to the thing I mentioned a little while ago. Writing a C program that can print out its own source code is a similar version of that. In fact, it was partially inspired by self-replicating cellular automata. So this is all like theory of computation stuff, and it's a big area that you may study when you take a course in like programming languages, for example. You might study different versions of computation that, you know, would probably include Turing machines and cellular automata and things like that.
If you, super unrelated, but another cool Google thing is if you look up Conway's Game of Life, it makes the background of the Google Conway's Game of Life.
Oh, that's nice.
It's really cool, actually.
I did not know that. I just found that out. That's super cool.
I'm not sure how to get to Google's page on it.
You just gotta type, just in the Google search bar, Conway's Game of Life with an apostrophe.
With an apostrophe. Interesting.
It starts on the edges and then kind of.
Oh, there we go. Yeah. All right. So yeah. So if you've done 101 with me, you've probably heard me talk about cellular automata, and it's a topic we could talk about in 215, but it didn't make the cut for topics that I cover in this course. But cellular automata is a worthwhile area to look at. And Game of Life is a particular type of cellular automata, and yeah, in the background here you can see cells turning on and off and kind of doing their thing. That's pretty cool. So this is a good thing to look into.
If you have dark mode, it looks even cooler.
Oh yeah?
Yeah.
Nice. All right, other questions? So appending a 1 to the rightmost end of a string, so, you know, assuming that we're sitting somewhere in the middle of our string to begin with, otherwise it's not very interesting. State 0.
Question though before
Yeah.
we begin there.
Sure.
When you say append, because I was like, well, appending normally means like you're putting it at the end or like that kind of thing, so we're not actually replacing it.
Right.
We replaced one of the B's.
Yeah.
Cool. Thank
Awesome.
you.
Yeah. So yeah, state 0, if there's a 0, stay in state 0, write a 0 and go to the right. State 0 and a 1, stay in state 0, write a 1 and go to the right. And so, you know, here we're trying to find the end of the string. If you're in state 0 and there's a blank, we can go to state 1. We can replace the blank with a 1 and doesn't matter which way we move. And so this will basically, you know, move all the way across until it gets here. It'll move one more spot, find the blank, and write a 1 in place of that. And then if state 1 is not defined, it'll just exit at that point. So you could do that with a 3-line program. State machine analysis. Did anybody figure out what this thing does?
My best guess was it finds the first, I don't know what it was, 1 or 0, and then moves to the left once.
Yeah. So we start in S0. If there's a 0, it becomes a 1, and we move to the right. So we're going left to right. And as long as we have zeros, they become 1s. If we're in state 0 and there's a 1, we change that to a 1, and we move to the right. And and we keep staying in S0, so if there's a 0, it becomes a 1. If there's a 1, it becomes a 1. And this will keep happening until we get to a blank. And if we get to a blank, we'll move to state 1. We'll leave that blank in place and go left. And if we're in state 1 and there's a 1, we'll go to state 2, write a 1, and move to the right. So, sorry, that would have been a 1. So it looks like what this does is it takes whatever bit string you have, it changes it to a string of all 1s, and it leaves the read-write head to the right of the least significant digit. So probably not the most useful function in the world, but you know, that's what it does. Alright, we assumed, we talked last time about a finite state machine to recognize a string containing the same number of zeros and ones, and we noted that is not possible because of the finite number of states. And that in fact it's not possible with a C program either because it has a finite amount of memory. And so we can't count indefinitely how many zeros and ones somebody has entered.
State machines can't count, right?
They can count, but there's a limit to how much they can count. It depends on your number of states.
That's what I'm saying. Yeah, they can't. You can't have 2 states that count more than 2 things or something.
Right, right. All right, and then let's go through 1, 2, 3, and 4. So, and again, for these questions, we didn't really specify what you should do if you get a string that's not recognized. Should you go back to the beginning? Should you go to a state where you sit forever and contemplate, or should we pick up a string partway through an unrecognized string, and the specific diagram will change based on that. But let's just do a first order. So we want to recognize 1, 0, 0, 1. So start in our initial state, and if you have a 1, go here. If you have a 0, go here. If you have a 0, go here. If you have a 1, go here, and this is a recognized state. So those transitions will successfully recognize this string. The question is, what happens if we get something that doesn't match this pattern? What if we get a 1, 0, 1, 0, 0, 1? Well, the easiest thing is, if we get a 0 here or a 1 here, just go to this, state of penance where we just say, nope, we didn't recognize it. But an easier option would be, or a more useful option might be to say, we've got a 1 and we've got a 0, and now we're expecting another 0. But if we get a 1, let's go back here. And I'm thinking this state means I've seen a 1. So if I'm in this state and I see a 1, I'm going to stay here. If I'm in this state and I see a 1, I'm going to stay here. Sorry. That state. If I'm in this state and I'm expecting a 1 and I see a 0, so I get a 1, 0, 0, but I get a 0 over here, I really need to go all the way back to the beginning and say, hey, I'm waiting for a 1. So I get a 1, which brings me here. If I get a 0, I'll come here. If I get another 1, I'll come back here. If I get a 0, I'll stay here. If I get a 1, if I get a 0, I'll go here. If I get another 0, I'll go here. And now if I get a 1, I go to my recognized state. And so it picks up that piece of the string. And so same idea, if you want to recognize any repetition, including no repetitions of 1 followed by 0. So our initial state is recognized because that's lambda, that's an empty string. And if we have a 1, we come over here, and if we have a 0, we go back here. And if we're in this state, if we got a 1 and over here we see a 0, we see another 1, then, you know, that could take us to our bad state. And if we're over here and we're expecting a 1 and we see a 0, that could take us to our bad state. And over here we can just stay in our bad state forever. And then question 3 is similar, except we need to start with a pair of 1s. So our start state, we'd need to have a 1 followed by another 1, and then we could come in here. And again, maybe if we have a 0, we'll take that to a non-recognized state, and if we have a 0, we'll take that to a non-recognized state. So now from our start state we have to have a 1 and a 1, and that's recognized now, and any repetition of 1, 0 will still be recognized. And then finally 0, 1 to the n, 0. And n is not specified whether it's bigger than or equal to 0 or 1. So we'll just assume n is bigger than or equal to 0. So here's our start state. If we get a 0, we'll go to a recognized state. If we have another 0, that's recognized. If we, well, this one's a little trickier. If we have a 0, that'll be a recognized state. And if we start off with a 0 and we get to this state here, and then we have a 1, we can take any number of 1s. And so this will eat up, you know, 1 to the n, and then if we have a 0, that'll take us down to a recognized state. This is not recognized. So there's a 0 and a 0, that's recognized. A 0, 1, 0 is recognized. A 0 followed by a bunch of 1s followed by a 0 is recognized. And what do we do over here? Maybe we would say if you have a 1 or a 0, we'll go to some bad state.
I'm curious about something.
Yeah.
For all of these, you're doing these giant ones, but it's only asking for that specific string. Are you just adding extra for the sake of it?
So a string like 0, 1 to the n, 1 means that we can accept the following strings. This, 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 and so on. So that's a shorthand for representing a infinite number of bit strings. Right, so a 0 followed by n 1s followed by a 0. Does that make sense?
Not really, because like you're including this bad state, but I'm just kind of like, that wasn't part of the 0, 1, 0.
Did we have to add the bad state?
Not necessarily. So what I mostly want to see is that if you input this string, you get to a recognized state. So for example, if you type in a 0 followed by another 0, you come to this state, which is a recognized state. Right? So it recognizes this string. And if your input string was a 0, a 1, and a 0, well, the 0 would take you here, the 1 would take you here, the 0 would take you here. That's a recognized state. So it recognizes 0, 1, 0. But for example, the string 001 shouldn't be recognized because it doesn't match this pattern. So that's why I have a bad state. A 0 brings you here, a second 0 brings you here. That's recognized. But then technically if I get another one after that, that's not recognized. But mostly I just want to know, you know, can you get to a recognized state when you have a recognized string? And as I said, these problems would have to be more rigorously defined if you were trying to make, you know, a machine that behaved perfectly the way the person wanted. They would have to tell you more information. Like what should it do if there's extra input after this? What should it do if there's extra input before this? What should it do if your string starts with a 1? Should it immediately go to a bad state? Or should it just hang out here, you know, waiting for you to type in a 0? In other words, should this be a recognized string because that matches our pattern? Or should it just say, nope, that doesn't match our pattern? Well, if we want to just throw it out as soon as it doesn't match our pattern, we can just have all these other things go to a bad state. And then our bad state, once you're there, right, you haven't matched the pattern, so you're never going to. But yeah, this is just a shorthand way of writing a whole bunch of patterns. So if you wanted to represent, you know, a number of bit strings like this, we can write this succinctly as 0, 1 to the n, where n is bigger than or equal to 1. And it means one or more repetitions of 0, 1, so that's this or this or this or this, and so on. All right, and the counting questions. So how many passwords are possible for the following criteria? So 4 uppercase letters with repeats allowed. So how many passwords can you do with 4 uppercase letters, repeats allowed?
26 to the 4.
Right, that's a product rule application. To pick a password, you have to pick the first letter, and then the second, and then the third, and then the fourth. And the number of ways you can do each of those tasks is 26. And so the total number of ways you can complete that task of picking 4 letters is 26 times 26 times 26 times 26. So that's 26 to the 4th. If no repeats are allowed, the same subtask, pick the first letter, pick the second, pick the third, pick the fourth. But this time, the way we can pick the first letter, we have 26 options. But to pick the second letter, we only have 25 options. So there's 25 ways to do that, and then 24 ways to pick the third, and 23 to pick the fourth letter. So we have a smaller number of ways to pick a 4-letter password with no repeats allowed. And this will be slightly smaller than 26 to the 4th. And then 4 uppercase letters must start with, yeah.
That's not going to be 26 exclamation point, right?
This, no.
It's going to be 26 over 4 exclamation point times 22, right?
This would actually be 26 exclamation over 22 exclamation.
Not times 4 exclamation.
Right. But if we think of it as a product rule, if we think of it...
minus 4, but I thought you multiplied it by 4 bang as well. Or bar bang.
Yeah, so you can do this with just a straight product rule and think of it in terms of subtasks. But if you want to think of it in terms of permutations, combinations, right, this is saying the order in which these things are picked matters. So it's a permutation question. And we're trying to arrange 4 things out of 26. So this is P 26, 4. And our formula for permutation says this is 26 factorial over 26 minus 4 factorial. So that's 26 over 22. Sorry, that was occluded. P26(4) is 26 over 26 minus 4 factorial. So 26 over 22 factorial. But this is really just right, that's 26 factorial. And this is 22 factorial. And so when you do this division, all of these things cancel, and you're left with just that part. Make sense?
Yeah, got this all wrong.
Okay.
Check.
Better now than Wednesday, though. So 4 uppercase letters must start with Z, no repeats allowed. So 4 uppercase letters, it has to start with a Z, and there's no repeats. So how many ways can we find a password like this?
25 times 24 times 23.
Mm-hmm. So we have to pick this letter, and there's 25 ways to do that. Then pick this letter, there's 24, and pick this letter, there's 23. So that's the number of ways we can accomplish those 3 tasks. Exactly. All right, 6 uppercase letters must start with ZQ, no repeats allowed. So now we've got ZQ, boom, 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 boom. And it's just a variation on that same idea. There's 24 ways to pick this letter, 23, 22, and 21. All right, and then E makes it a little different. 6 uppercase letters must begin with a Z or a Q, and no repeats allowed.
2 times permutation with 25 5 is what I was getting.
Perfect. So what's happening here? We have a sum rule. We can complete this task one of 2 possible ways. The first way is to begin with the letter Z, in which case we have 25, 24, 23, 22, 21 ways to fill in the rest of this. Or, you know, we can permute 5 things out of the 25 letters that are left. But the second option is to begin with a Q and then fill in these 5 spaces, and we can do that same number of ways.
Your block, by the way.
Thank you.
Yeah.
Start with a Z and fill in these, or start with a Q and fill in these. And a sum rule says since we're allowed to do this or this, we're going to add those together. And so we get 2 times 25 times 24 times 23, 22, 21. All right, how about functions? We're mapping from consecutive integers from 1 to n into the set 0, 1. And how many possible functions are there? And there's no restriction on these functions other than they have to be functions. So how can we picture this? Say again?
2 to the n.
2 to the n. So how do you get that?
There's 2 things, 0 and 1,
Mm-hmm.
and then just n number of functions. I don't know.
No, I mean
Not
that's
really.
pretty much it, right? So the task of creating a function can be described as the following. Tell me what f of 1 is, tell me what f of 2 is, tell me what f of n is. If I tell you what each of these maps to, I've defined that function. And each different way that I can answer these question marks gives me a different function. So how many ways can I decide what f of 1 is going to be equal to? Well, there's only 2 options. It's going to be a 0 or a 1. So I've got 2 ways to complete this subtask. I've got 2 ways to define f of 2, and so on. I've got 2 ways to define f of n. I have n of these, And so I have 2 multiplied by itself n times is 2 to the n. That's how many functions there are. And that's a good old 250 flashback. All right, we did number 4 last time. That's pigeonhole principle. And then the duck race. So 6 ducks running a race. Has anybody here ever seen a duck race?
I
No.
feel like it'd be like herding cats, so.
I've seen a chicken race.
Chicken race, probably the same idea. Where'd you see a chicken race?
Video game.
Ah, okay. I saw duck races at North Carolina State Fair long time ago, and it was the funniest thing because they obviously trained these ducks, and you know they told the audience that like when your duck passes your section, if you thump really loud on the side, your duck will like that and will run faster. And they trained these ducks to like do this, you know, when they hear this sound, and yeah, it was pretty funny. And they told us they retired the ducks after 1 season. And they like let them live out their lives on a farm. I don't know if it's true or not, but it was cute.
I have seen a wiener dog race.
Oh my gosh, that would be awesome.
It was adorable. They were in costumes.
I will have to look that up on YouTube later. That's gonna go over really well with a 9-year-old, I know. All right. All right, so duck race. So no ties are possible. How many finishing orders are there for 6 ducks? So what kind of problem is this?
Isn't it just no repeats, permutations, or whatever?
Yeah. So we could do this as the product rule, or we could do it as a permutation, right? The task of finding the finishing order is a question of deciding who comes in first, who comes in second, who comes in third, and so on, and who comes in 6th. And there's 6 ducks we can choose from for first place, 5 for second place, 4 for third place, and once we've picked all of the first 5 places, there's only 1 choice left for 6th place. So this is 6 factorial. But we can also go straight to a permutation argument and say, hey, this is an ordered arrangement of 6 ducks taken from a group of 6. The order matters, so this is just P6 comma 6. Which is 6 factorial over 6 minus 6 factorial. 6 factorial over 0 factorial, we're back to where we started. 6 factorial over 1, that's just 6 factorial. All right, any other questions on any of that? All right, let's go ahead and take a short break, and then when we come back, I'll just run through a brief final exam guide, and we can ask questions along the way, but we'll just kind of do that to wrap up. So we'll come back in just over 5 minutes. seconds. All right. Any other questions from anyone before we do kind of a general review? All right. Well, this is a tentative study guide, so let's go through this and we'll make adjustments to it as we talk through it, and then I'll post this on Canvas right after class. So some of the things that we've done. Well, let me talk about the exam first of all up front. So your exam is on Wednesday from 1 o'clock to 2:50. Right, and it'll be the same mechanics as the midterm. So it'll be a file you download from Canvas, and it'll have a series of questions. You write up your answers, upload a scan of them as a PDF by the deadline, taking into account any time allowances if you have any. And if you have a time allowance, don't worry if Canvas says it's late, because Canvas doesn't know about those adjustments. And there'll be the usual honor statement in the beginning about not using other resources and so on and so forth. And so for the final exam, we're doing this on the fly here. So the final exam will be open note. You got 6 double-sided pages or 12 single-sided pages. So lots of space for notes. And that's all you're allowed to use, no other resources. All right, again, I recommend you hop into Canvas during the exam so that if there's errors or clarifications, I can announce those in Zoom. So hop into Zoom during the exam. Any questions about logistics? When it is, how to turn it in, that kind of stuff?
More interested in what's going to be in it.
All right, well, let's go through a list of possible topics.
Is the study guide going to be on Canvas?
Yeah, once we get through this, and I might make some changes here, and then I'll post it on Canvas as a PDF right after the exam item. So it'll be in the module called Final. So we start off by talking about sets. You should know, the basic definition of a set. Different ways to represent sets. Some of the standard sets that we've worked with, Z and Q and R and so on. We talked about operations on sets, so ways to combine sets, unions, intersections, complements. Try to keep these straight. If you're unsure, put them on your note sheets. This is a union. This is combining everything that's in the two sets. This is an intersection. So this is, combine. Intersection is where we look for the overlap. So we're looking for things that are in A or B. We're looking for things that are in A and B. And if you get those two reversed, you probably end up losing a bunch of points on set theory questions because of a simple misrecollection. So make sure you understand which is which. These two symbols are for subtraction or complements. And these are both the complement of B in A. Or sometimes we might call it A minus B, or A take away B. But it's not a mathematical subtraction operation. If these are sets of integers, we don't subtract these integer values from those integer values. This is a set operation. We can have, a set of puppies and another set of puppies, and we can subtract them. We don't mathematically subtract one puppy from another. We start with this set, and we get rid of everything that's also in this set. Right, so it's a complement operation. And if we start with the entire universe and we take away B, we can also write this as B with a little subscript, a little superscript of C, or we can write it as B with a bar on it. And this is just called the complement of B. So this symbol is the complement of B in the universe. And it means all the things in the universe, but throw away all the stuff that's in B. So it's everything that's not part of B. It's the usual sense of a complement. And you're very likely to have a set theory question on the exam. And everybody knows these concepts. Everybody can do these operations. Don't lose points needlessly. Right? Don't forget what this means or this means. Right? Put it on your note sheet. Go back and look at it in the text. And if I say, what's the complement of this set and that set, just start with this set, throw away everything that's in there, and you got points for it. If I ask for the union of two sets, just write down everything that's in either set. Don't list things more than once, though, right? If I ask for an intersection, tell me the things that are in both sets, and so on. So complements universe. We talked about the empty set. The empty set is a set that doesn't contain anything, right? So it's a set with no elements. You should know about the size of a finite set. That's what we call cardinality. I won't ask you about cardinality of infinite sets, all the weird stuff with Hilbert's Grand Hotel and stuff like that. I'm not going to ask you about those. But if we have a finite set, we can write this as a symbol for the number of things in that set, or the size of the set, or the cardinality of the set. So just count up the number of elements. If a set has no elements, that's what we call the empty set. Subsets, so subset contains some or all of the elements in another set, but it doesn't have anything that's missing from the original set, so it's a subset, right? Power sets. The power set is itself a set, and it's a set containing all subsets of, in this case, set A. So A is a set, power set of A is another set, and it contains all the subsets of A. Cartesian product, which was the idea of tuples. So A cross B will be the set of all tuples comprised of a little a comma little b, where little a comes from set A and little b comes from set B. And the kind of prototype for that is to think of Cartesian coordinates. And then set identities, these go along with the identities we learn in Boolean algebra in 250. So, you know, A union B equals B union A, it's commutative. A complement, complement is the same as A, double negatives. Things like that. A union the empty set is A intersect the empty set is empty, and so on. Alright, functions. Remember, functions are maps from one set to another. So here's a set A, here's a set B. Here's a function f that takes points in A over to points in B. And to be a function, all it has to do is take each point here to a point there. But it's possible that it could take multiple points in A to the same point in B. Or it could be that different points in A always go to different points in B. And so this is a property we call injectiveness. If a function is injective, it means different points in A go to different points in B. It's also possible that there are some points in B that are not mapped to, or it could be that every point in B is mapped to from something. So if every point in B is mapped to, we say the function is surjective. And if it's both of these things, it's bijective. So these have to do with sort of the nature of this mapping from A to B. Domain is the set of things that you map from. Range is a set of things that you map to. And to be well defined, we need to know that, you know, things in A map to exactly one thing in B. If A were to map to two different things in B, it's not a function anymore. So like an inverse sine is not a function in the actual sense, because the inverse sine of 0 is both 0 and pi and 2 pi. A pure square root is not a well-defined function, because the square root of 4 is both 2 and minus 2. So if a point here maps to more than one point in B, it's not a function. So that's the requirement for being well-defined. Alright, we talked about summation, so this you know, sigma symbol sum from I equals A to B of some function f of I. And it's calculate f of A plus 1, f of A plus 2, all the way up to f of B, and just add them together. And this corresponds to a for loop with a running sum. We can do double summations. And this is like a pair of nested for loops. So figure out the inner expression first, and then apply the outer summation to it, and so on. We touched briefly on matrices. I'm not going to ask you a lot of details about matrices, but here's something we talked about. It's a way to you know, have a series of numbers, for example, that look like this, and we can define addition, subtraction, multiplication, and so on. But we did this mainly as an example of some things we can do with summation, so I won't ask you. In fact, I'm just going to go ahead and put a strike through on that, so don't worry about matrices. Alright, but definitely worry about propositional logic. This has been like, you know, a core of the course. So, definitely know what a proposition is. Right, a declarative statement that has a truth value. And we take propositions and combine them to get new propositions. So how do we combine propositions? We can AND them, that's conjunction. We can OR them, that's disjunction. We can say one proposition implies another, that's A implies B. Or a conditional statement, like that. If A, then B. Rules of inference and logical equivalences. So page 58 and 59, or 57 and 58 from the text. Go through those. Anything that you're not familiar with, make sure you put those on your note sheet. Or, if you got the page budget, just print out those pages. And so these are things like, P and Q is equivalent to Q and P. Or P implies Q and P implies Q. This is called detachment. P implies Q and not Q implies not P. This is called indirect reasoning. So all of those rules that we end up using in proofs, right, those are what I'm referring to here as rules of inference and logical equivalences. Quantifiers are things like for all and there exists. And so typical forms would be, for all x contained in Z, some proposition of x is true. Or there exists an x contained in Z such that P of x is true. Or maybe there exists a unique x contained in Z such that P of x is true. So those are quantifiers. And fallacies, two fallacies we talked about: denying the hypothesis and affirming the conclusion. So make sure you know what those are. They're kind of the opposite of detachment and indirect reasoning. All right, we studied propositional logic so that we could talk about proofs and do proofs. And there's two main methods of proof: direct and indirect. Indirect proofs are also sometimes called proof by contradiction. So a direct proof, start with what you know, argue until you've shown what you're trying to show. Indirect proof, start with what you know and the negation of what you're trying to show, and work until you find a contradiction. All right, proofs about even, odd numbers, good fodder for proof questions on exams. Also divisibility. So proofs about even and odd numbers, or divisibility. And the idea to keep in mind with proofs is, start with what you know and work to what you don't yet know but you're trying to show. And when's it all right to start with what you don't know? Well, for example, if you're trying to prove that, A implies B, it's okay to start off by assuming A is true. We don't know if A is true, but our goal is to prove that if A is true, B is true. Well, to do that, we're probably going to make the first step of our proof be A, and the reason is that's a hypothesis. And then we do whatever else we have to do and work forward, and eventually, hopefully, we come up with a statement that says, hey, B is true, and then we're done. And be really sure that you know how to write a proof. And if you've lost points or gotten feedback on homeworks or on the midterm and so on, right? Make sure that you know how to do a proof, because I'm very much interested in how you present a proof. Not just, do you know how to turn n times n plus 1 over 2 plus n plus 1 squared into this other expression, right? how are you going to use that knowledge to prove, this formula about the sum of consecutive integers, for example? That's what I'm looking for. I'm looking for the ability to, present a proof logically. Everything is a proposition. These are numbered. There's justifications for each statement, referring back to previous propositions and laws of inference and so on and so forth. So we got office hours tomorrow morning from 8 to 10 and Friday from 9 to 10. So you got 2 more chances to come in and go over this stuff with me. Take advantage of them. All right, number theory. So we talked about divisibility, and remember, this is a funny notation. D vertical bar n means D divides n. This is not division. This is not taking n and dividing it into D. This is saying if I take n and divide by D, I have no remainder left over. It means there exists some integer I such that n equals D times I. It's a proposition. It's a claim that there is an integer I such that this is true. It's a proposition involving an existential quantifier. It's all this stuff we've been doing about. All right, so divisibility, definition, examples, uses, congruence. So congruence is looking at remainders when things are divided. And there's 2 ways to look at congruence. A is congruent to B mod M. Means exactly the same thing as M divides the difference of A and B. So if the difference of 2 things is a multiple of M, those things are congruent modulo M. But there's this thing called the division algorithm, which says that if we take one number and divide it by another, we can find a unique thing which is congruent to this number. So if I take the number 17 and I work mod 3, I can find lots of things that are congruent to 17 mod 3. It's congruent to 20, it's congruent to 14. It's congruent to 2. It's congruent to -1. There are many numbers whose difference from 17 is a multiple of 3. The division algorithm says there's exactly one such number that's bigger than or equal to 0 and less than the moduli 3. In this case, it's the number 2. Alright, we talked a bunch about primes, what the definition of a prime is. It's a number bigger than 1, not divisible by anything except itself in 1. Fundamental theorem of arithmetic, which is that numbers can be written uniquely as products of primes, positive numbers. Euclidean algorithm for finding greatest common divisors. So you did that on some homework questions. Didn't look like there was any problem with that. Modular exponentiation and Fermat's little theorem for doing large exponents modulo some number. And you did those in homework questions, and that seemed to be fine for everybody. But certainly go back and review all of your homework. Anything that's come up on homework assignments is potentially good material for an exam. Which means if you can do all of your homework questions on Wednesday, you're probably in good shape for the exam. It also means if you completely forgot everything about set theory and modular exponentiation and propositional logic, right, you may have a trouble with some of the questions on the exam. So go back and review all of your homework. And then applications of all of this stuff. So we talked a little about parity and check digits with ISBN codes and things like that. I'm not going to ask you any details about that. But those are, some applications. The bigger application we talked about was cryptography. And we looked at, Caesar cipher, which is a replacement cipher, shift cipher, symmetric versus asymmetric public key ciphers, up to and including RSA. And certainly I'm not going to ask you details of, implementing a public key cipher or doing an RSA encryption or anything like that. But you should understand that most of these ciphers, if you know how to encode, you also know how to decode. It's the same password for both operations. Those are called symmetric. An asymmetric cipher has two keys, one for encoding, one for decoding. And so these are called public key ciphers. You can publish the key that's used to encode, keep secret the key for decoding. And now everybody can send you coded messages. You're the only person who can decode them. So that's what makes the web work. Chat question. You talked way back in the course that we can expect some kind of curve at the end. Possibly. It kind of depends where grades come out, but typically there's some sort of curve. But it's hard to speculate ahead of time. But I will say, if you do well on the final, you should be in pretty good shape. But what constitutes well, I don't know exactly. Certainly, if you miss the final, you're probably not doing well. So don't miss the final. But show up and do the best you can, and we'll figure it out from there. Alright, and then we looped back and we talked about mathematical induction. And this was the part that most sort of critically ties into computer science. And it ties into recursion. And so induction, remember, there's two steps to doing an inductive proof. You prove a base case, you prove an inductive step. But before you can do that, you need to do some setup, right? You need to state what it is you're trying to prove. You can't just launch into a proof unless you've told, the reader what it is you're trying to prove. And usually what you're trying to prove is a family of propositions. Or, some statement about a set of integers. So, for example, prove 1 plus 2 plus 3 plus ... plus n equals n times n plus 1 over 2 for all n contained in Z, n bigger than or equal to 1. So that's a clear statement of what I'm trying to prove. And that's, typically what you'd be given on an exam, right? That would be the question, prove this. Don't ever start talking about, P of 1, P of 2, P of n, if you don't first tell the reader what the heck P of n is. You know what it is in your head, but the person reading your proof can't read your mind. So you're probably talking about a family of propositions. So define what that family of propositions is. So let P of n be the proposition. Okay, it took me 10 seconds to write that. Spend the 10 seconds. Don't say P of n equals. Let P of n be the proposition. Don't just draw an arrow up here. Because I don't know if you're talking about that, or this whole thing, or the equal sign, or what. Let P of n be the proposition 1 plus 2 plus 3 plus ... plus n equals n times n plus 1 over 2. And I can say n is contained in the integers, but this is not the proposition that this is true for all n. Right? N is a wild card. P of n is the proposition that this is true for n. P of 5 is the proposition that this is true for, n equals 5. It would make no sense to say this is true for all n, because P of 5 would say, this is equal to that for all 5 bigger than or equal to 1. And that doesn't make sense. So P of n is this proposition. But now our goal is to prove P of n for all n bigger than or equal to 1. And now you're set to start the part that most people want to rush into right away, which is step 1, our base case. And before I write the proof, I'm going to state what it is I'm trying to prove. I'm going to prove P of 1. Now I'm going to write the proof. P of 1 says 1 equals 1 times 1 plus 1 over 2. And I'm just going to note now that 1 times 1 plus 1 over 2 equals 1 times 2 over 2 equals 2 over 2 equals 1. And so this P of 1 basically says 1 equals 1, which is true. So P of 1 is true. And I can't tell you how many times I've gotten homework or midterms where I say prove this, and the first thing I see is this. P of 1 says 1 equals this, P of 1 is true. And there's no definition of what P of n is, or what P of 1 is, right? So spell it out. And this will help you write a better proof. It's not just, dotting the I's. This will help you as you're going through your proof to remember what P of n is and what it is that you're trying to prove. And mostly what we're trying to prove after the base case is the inductive steps. So we want to prove P of n implies P of n plus 1, where n is bigger than or equal to 1. And so now this is the part that resembles the kind of proofs that we've done. And we're trying to prove if this, then that. So typically our proof begins with the hypothesis. P of n, that's the hypothesis. And then you're off and running, and you do whatever you got to do until eventually you prove P of n plus 1. Why? Well, there better be some reason here which uses some combination of previous statements and some sort of rule of inference. And every statement you write after this hypothesis has got to follow from the statements you've already written, or some kind of rule of inference, or some basic fact about algebra or integers or something like that. And then when you're done, right, and you've proven P of n plus 1, then you can say, therefore, P of n for all n bigger than or equal to 1, and the reason for that is mathematical induction. And then and only then are you allowed to say, that's what I was trying to demonstrate, QED. So for inductive proofs, I would say probably where your time is best spent in preparing for these is thinking about how you're going to present the proof, right? And I'm going to try not to give you something that's horribly complex to make the leap, like the factorial questions we had on homework, right? Those are pretty complex to figure out, well, why is this thing equal to that thing, right? I'm probably going to give you something that's going to be more straightforward math-wise, but I want to see the well-made presentation of it. Alright, so that's what all of this is. Stating the proposition, the base case, the inductive hypothesis, and conclusion, how to logically reason from what you know or assume. Alright, recursive functions, we talked about a little bit. We didn't do a whole lot, but mostly that's a tie into 222. But basically, there's two pieces to a recursive function. There's some kind of, something like a base case, something which we begin with, and then some kind of inductive step or recursive step, which gets us from the base case to some other value. So, for example, somebody's solution for that first homework question, right? Here's a definition of n factorial. This is like a base case. If n is equal to 0, this factorial is equal to 1. Otherwise, we can define it in terms of other values of this factorial function. In particular, n minus 1, we can turn that into n factorial by multiplying by n. And this should at this point, be seeming very familiar, right? A recursive function is a base case and a rule that expresses the value at some integer in terms of values at smaller integers. This is the knapsack problem, right? How much stuff can I put in a bag that holds 10 pounds? Well, if you tell me what I can hold in a bag of capacity 8 and 7 and 3 and 2 pounds, I can combine those answers and tell you how much I can put in a bag that holds 10 pounds. So a recursive function, we express the value at some point in terms of values at smaller arguments, smaller integers, and we combine those, right? So this is what we do all the time with recursion. What's the height of this tree? Well, I don't know. Here's a smaller tree. Here's a second smaller tree. Tell me what the heights of those trees are, and I'll tell you the height of the bigger tree. Is this tree balanced? Well, I'll tell you what. Here's two smaller trees. Tell me if those are balanced, and tell me their heights, and then I'll answer your question, right? So our balance function, our height function, those are recursive functions. And they're so named for the same reason we use recursion when we code these functions in a language like C, because they're self-referential. It's defining the value of this function in terms of other values of the function, typically smaller values. All right, and then counting, we talked about the pigeonhole principle, and that's just the idea of, n boxes, n plus 1 objects, you're going to have at least one box containing 2 objects. So it's putting things into boxes, and the whole trick here is sort of figuring out how to envision a problem in terms of boxes and objects. Whether it's, finding integers that add up to 11, or, finding people who have the same first and last initial, or whatever. It's basically putting objects into boxes. So counting in general, so there's the product rule. When you can break a task into a succession of tasks, you multiply the number of ways to do each task. That's the number of ways to do your whole process. The sum rule says if you can do a task as either one of a set of rules, a set of procedures, you can find the number of ways to do each procedure, take the sum of those, that's the number of ways you can do the full procedure. So this is multiplication, this is addition. This is doing a bunch of things ANDed together, this is doing a bunch of things with an OR between them. Do this, or that, or that. Principle of inclusion-exclusion was this idea that if you have two sets and you combine them, the number of things in that combination is the sum of the number of things in each set minus the number of things that overlap. And we can use that to answer questions about, 200 people went to see Star Wars and 150 people went to see Superman. And this many people how many people went to see both, or something like that. All right, so the general version of these sum and product rules take us into what are called permutations and combinations. Really, really important. Remember, permutations are ordered, combinations are unordered. Right, so permutation is saying, how many ways can I do something if the order in which I do it is important. How many ways can I pick 3 objects out of 10 if the order in which I pick those is significant. If picking items 1, 3, and 7 is different from picking items 7, 3, and 1. Right, that's a permutation. If we don't care about the order, if you just want to choose 3 items and it doesn't matter in what order you chose them, that's a combination. And we have some handy formulas for doing permutations and combinations. So ordered collections, this is an R permutation of n objects. So we're picking R things in order from n. This is n factorial over n minus R factorial. And that comes directly out of the product rule. There's n ways to pick the first thing, n minus 1 to pick the second, n minus 2 to pick the third. Take all those numbers, R of them, to pick all R objects, multiply them. This is a formula for what you get. when we do combinations, and remember we can write combinations with this funny notation. So this is n choose r. That's the same as the number of permutations divided by r factorial, which is the number of ways we could arrange the things that we picked. And so if you plug this formula in for this, you get n factorial over n minus r factorial times r factorial. And so this is generally a smaller number than the permutations, because you're dividing out by r factorial. And then we played a little with Pascal's triangle, which is basically a triangle shape that shows us values of combinations. And so it looks like this. And each number is the sum of the two numbers above it, basically. But these turn out to be the values of this choice function. This is C00, 1011, 20, 21, 22, 30, 31, 32, 33, and so on and so forth. And then the binomial theorem is just the observation that these are also the coefficients when you raise something like a plus b to the fifth. For example, we're going to get something times a to the fifth. We're going to get something times a to the fourth b. We're going to get something times a cubed b squared. We're going to get something a squared b cubed. We're going to get something a b to the fourth. And we're going to get something b to the fifth. So what goes in these coefficients in front is these numbers right here. So that's what the binomial theorem tells us. If we look at the choice function, these coefficients will be 1, 5, 10, 10, 5, and 1. So you can impress your friends by multiplying binomials by themselves. All right, and then the last topic, which we talked about the last week or so, was grammars and languages. And so we talked about the idea of syntax versus semantics, and we were interested in syntax, structure, not meaning. So we can construct, C programs that are gibberish that will segfault right away or do nothing, but are still syntactically correct, will still compile without error, without warning. We can make sentences that are ridiculous, right? We can play Mad Libs and come up with a story comprised of perfectly correct English, but that has, ridiculous meaning. So we're only talking about the structure or the syntax of a language here. And the main way we studied for describing languages was this thing called a phrase structure grammar. And so this was a four-tuple where we had a vocabulary, a set of terminal symbols, a start symbol, and production rules. And we could go from the start symbol to words over the language. And we can do two things. We can analyze a phrase structure grammar, or we can try to write a phrase structure grammar. The analysis goes from a grammar to a set of words. The synthesis goes from a set of words to a grammar. All right, we revisited finite state machines with a hopefully kinder, gentler approach than from 250. We talked about state diagrams and being able to analyze a state diagram to see how a machine changes from state to state for a certain input, and we talked about designing state diagrams to achieve a certain behavior. And in particular, we looked at state machines and how we can use them to recognize types of input strings. So find a string with an odd number of ones. Well, we can make a state machine for that. And most of our state machine synthesis was limited to drawing a state diagram, right? We didn't do flip-flops or things like that. And then Turing machines are a particular example of a state machine, and it's the one, from which von Neumann architectures, our current machines, basically come from. And that was, part of this last homework set that we went over in the beginning of class today. So present state, input symbol, next state, output symbol, and movement, left or right. And using that kind of of setup, we can basically implement state machines to do whatever kind of recognition or manipulation tasks we want. So I think that's a pretty good synopsis of what we've been doing the past 10 weeks. And so I'm going to go ahead and save this and post it on Canvas. Let me do that right now. Hold on one sec. Alright, so that should be posted on Canvas in the final exam module. So that's just a synopsis. It may not be 100% complete, but I think it's the highlights for what we've done. And again, I strongly recommend go back over your homeworks. Those are an excellent source of exam questions. And I probably won't give you, exactly a homework question, but I might give you, variations on questions you've already done in homework. So if you're comfortable with how to solve the homework questions, you're probably in pretty good shape for the exam. All right, other questions or comments or thoughts? Yeah.
Could you go over doing a proof in like number theory or something like that? The exact form I always never seem to remember how to do.
Like a divisibility proof, maybe?
Yeah, something to do with number theory or something. I don't know exactly all the proofs we did. I kind of forget. But
So I think the only proofs we've done around number theory were probably divisibility.
Yeah, I think so.
So let's look at a sample question like that. Proof. Let's do if 3 divides n, then 3 divides n squared. Where n is an integer, we'll just do n as an integer. So prove that if n is divisible by 3, then n squared is also divisible by 3. So, we can test this. I mean, 9 is divisible by 3, so is 81. 6 is divisible by 3, so is 36. So this seems plausible. We're not going to have to use induction on this, right? We could try to do it with induction, but usually I'll say, write an inductive proof if I really want you to do that. So how could we prove this? This is a conditional proposition. It says if this is true, then this is true. Each of these is a proposition, and we're trying to show if this, then that. And the only way you can ever prove if this, then that is to start off by assuming this, right? Unless this is something that's always true, right? I could say if 3 divides n, then 1 plus 1 equals 2. Well, we might be able to show that directly. But presumably we've got to assume this. So our first step of a proof is usually going to be whatever the hypothesis is. So I'm going to state 3 divides n, And the reason is that's my hypothesis. I'm assuming that's true. And I want to go on and prove things after other things until eventually I prove 3 divides n squared. Alright, well, I've got a 3, a pipe, and an n. I don't really know how to do anything with that. I need more stuff. So I'm going to change this into what this divisibility proposition actually says. This actually says there exists an integer I such that n equals 3i. That's the definition of divisibility. So that I'm saying is true because I'm assuming it's true. It's my hypothesis. And if this is true, then there is an integer I such that n equals 3 times I. Right? That's what this means. So this is certainly true given that statement 1 is true. And, you know, maybe I'll go to an ignore section and I'll say, hey, I'm trying to show 3 divides n squared.
Wait, so that's definition of I?
That's the definition of this divide symbol. Or definition of divides. Yeah. So I'll come over here and I'll say, you know, I'm trying to show n squared equals 3 times some integer. Right? If I can do this, then I can say 3 divides n squared. Well, I've shown n equals 3 times one integer. How can I show n squared equals 3 times some possibly different integer? And I'm going to sort of do some scratch work over here and say n equals 3i, n squared equals 3 squared, I squared equals 9i squared. Is there some way I can show that this can be written as 3 times an integer? And hopefully having done things like this before and thinking about it and having a good night's sleep, right? I'll look at this and I'll say, oh, wait a minute, this is equal to 3 times 3i squared, and that sure looks like an integer. So yeah, I think I can write n squared as 3 times an integer. And if I can do that, then I can say 3 divides n squared. So now I got to put that into the form of a proof. Well, I've shown n equals 3i. I can say n squared equals 9 times I squared equals 3 times 3i squared. And that's just algebra and using this proposition from 2, the fact that n equals 3 times I, tells me n squared equals 9i squared, which is 3 times 3i squared. And now I'm going to make the observation that 3 divides n squared. And why is that? 3i squared is an integer. And looking at step 3, I've said n squared equals 3 times this thing, which is an integer. And, you know, definition of divides. So this follows from that. And that's what I was trying to show. So I can stop right there. I can say that's what I was trying to demonstrate.
Did you use a step about closure of integers?
So 3i squared is contained in z. I could put something down here and say, you know, closure of ints, or I could put a separate step in here, right? I could put a step in here that says 3i squared is an integer, and the reason for that would be closure of integers. And then I could say 3 divides n squared because this says n squared is 3 times that, and this middle step says that's an integer. And as long as you've got the pieces in here, you're probably good, right? I've stated that 3i squared is an integer, and that I've shown n squared is 3 times that. That's my definition of 3 divides n squared. And that's what I'm trying to show, and so I can say QED at that point.
Okay, and so number 2 is for all of I, right?
This says there exists an I such that n is equal to 3 times I.
Okay, thank you.
Yeah. All right, other questions, requests, thoughts?
Can we go over one more example of the FSMs?
Yeah,
in
yeah.
our homework?
Let's see. So, like a recognition problem, maybe?
Like the second part of our homework, 1 through 4 or 5.
Okay, so I think those were making machines that recognized particular strings.
Mm-hmm.
So let's make a finite state machine that recognizes strings with an odd number of ones. So we don't care how many zeros we have, but if we have a string with an odd number of ones, we want to recognize that. And so I would start off in some initial state, and the empty string does not have an odd number of ones. It has 0 ones. So the empty state is not recognized, the empty string. And if we're sitting in this state here and we get a 0, well, as long as we're just getting zeros, we've got a string with a bunch of zeros but no ones. That's still not an odd number of ones. But if we find a single one, that's going to take us to a recognized state. So now we've got a string with an odd number of ones, in particular a single one. And if we're in this state and we keep getting zeros, we've still got an odd number of ones, right? We got maybe a bunch of zeros and then a single one and a bunch of zeros. That's still a string we want to recognize. But if we get another one, well, now we're in a state where we've gotten an even number of ones. And so this is not a recognized state. And if we get a bunch of zeros in here, that's not going to change anything. But if we get another one, that'll take us back to our recognized state. So what does this machine do? You can get a bunch of zeros, you're unrecognized. You get a single one, you're recognized. If you get a second one, you're not. If you get a third, you are. If you get a fourth, you're not. If you get a fifth, you are. So anytime you have an odd number of ones, you're going to be in this state. And whatever state you're in, if you get zeros, it doesn't change your state. So this is my starting state. This is a state where I've got an odd number of ones. This is a state where I've got an even number of ones.
Could you not just loop back to your original
Yeah, I
state?
could have just done this with 2 states, actually.
Okay.
Thanks.
Yeah.
All right, does that make sense?
Thank you.
Welcome. Let's see. Can you give a range on the number of problems? I really don't know. I have not written the exam yet, and I've got the list of topics I gave you, and I'll pick some stuff from there. I'll probably go heavier on the stuff since the midterm, but probably not too heavy on the very last stuff. So I don't know, there'll be a counting question, there'll be some kind of automata theory question, there'll be a set theory question, there'll be 1 or 2 proofs, there'll be some kind of number theory question, so, you know, at least 6 questions with some different parts to them, and then maybe
What's
some...
automata theory?
Sorry?
What's automata theory?
Languages and such.
Okay. Oh, like on state machines and whatnot, or?
Yeah, the last homework set.
Oh, okay, thank you.
So yeah, you know, probably several questions with probably multiple sections to them, and then And then maybe some, like, shorter answer, lower point questions, like some matching or fill in the blank or something like that. So I don't know, several questions, 10 questions, I really don't know. I got to write it up, but hopefully it will be doable, well within an hour and 50 minutes. And yeah, there's no class next Monday, so today's the last day of class for us. And for the Monday, Wednesday 222. Tomorrow's the last day for the Tuesday, Thursday 222. And next week is all just exam week. I don't have scheduled office hours next week. I'll start them after finals are done. I'll probably do 1 or 2 hours a week, mainly for advising, but I'll post those on the usual web page.
So I'm guessing this final is going to be handwritten, right?
By you or by me?
By us.
Yeah.
Answering.
Yeah.
Are we expected to maintain the same sort of neatness as on the homework? Because sometimes it takes, I spend a lot of time trying to keep my pages neat, but like scrapping a page and starting over and like rewriting all my answers if I make like a lot of mistakes on the page and I didn't want to have a bunch of scratch marks or whatever.
So I'm going to say be reasonable, right? So, on homeworks you're not allowed to scribble things out and so on. On an exam, if you make a mistake at the end, you don't have to start writing over from the beginning. But be reasonable. Ask yourself, when this is being graded, is Nick going to be able to follow what I did, right? And if I can follow your line of thought and I can, trace your steps and find your answer without being you're probably okay. But my bigger concern would be, try to set things up appropriately ahead of time. Use a soft pencil on clean sheets of paper, right? If scanning your paper, shows me a bunch of stuff that's on the other side because you're reusing your physics homework or something, and it's impossible for me to read because there's inclined planes and cylinders all over it, that's really hard, right? And it makes it difficult if you've got an answer wrong to figure out, well, how close were you and so on. So, clean paper, good soft pencil that makes a solid mark, a way to scan so that it's easily legible. And those are probably more important than, if you have to redo a section of your proof 5 times, well, just cross it out cleanly and make sure I can get to the section that you want me to look at. And as long as it's reasonable, you're good. All right, well, we got 5 seconds left, so I'll let everybody out early. And have a good rest of the week if I don't see you in Thursday class. And I will see everybody next week. Have a good one until then. Come by office hours if you need to talk. And thank you for the course. Thanks for your attention and energy. It's been fun for me at least. So I appreciate it.
Thank you.
Thank you.